Capstone, Newton. Okay, so my inspiration for this project is, I'm sure this is a universal experience for any band kid or musician here, but when we're tuning, our band directors usually have this little app on a phone that has tiny little lines when you're trying to tune, and reading those tiny little lines in the 0.5 seconds that he brings the tune around is impossible. So what I wanted to do to fix this is make a Loom Tune. And basically, Loom Tune is your average tuner, but it has a box with lights on it instead of the little lines, and those lights represent your tuning status, so it glows different colors depending on what tuning status you have. So before I begin, a little bit about me. I'm Nivedha. I'm a senior at Grandview High School, and in the fall I plan on majoring in electrical engineering at CU Boulder. I've taken 12 APs so far, some of which are AP Computer Science A and Principles, Physics 1, and Calc BC. I've also volunteered for Steel City Codes, and I'm a part of NHS, Math, Honor Society, Women in STEM, Wind Ensemble and Marching Band, and outside of school I like to do taekwondo. So for my expert advisors for this project, I have my dad, Souresh, who has a master's in computer science and is a senior software development engineer at Travelport, and he has experience working in different countries all over the world. And my second expert advisor is Northern Korea who's an industrial engineer and solution architect for NXP Semiconductors. So for my support advisors, I have Chelsea Mitchell, who is my emotional support, creativity advisor, and English spell check, who was also my inspiration for this project, as she gave me the idea. My next support advisor is Scarlett, who was major help with creating the box and 3D printing and SolidWorks, and was also emotional support. My mom, Sonia Tony-Thermal, who is a creativity advisor and emotional support, and my lovely woman in STEM table, who helped keep me on track and helped me stay focused. So for my company logo, I decided I want something sleek and simplistic, but also referenced my project. So I came up with this, and it has 3 LEDs to represent the 3 LEDs on my project. It has my company name, and it has 5 strings on it, which represent a guitar, because I wanted to reference to a musical instrument as well. Now, obviously, I wanted to get a lot more out of this project than just a tuner, so these are my project objectives. I wanted to learn more about music theory and to increase my musicianship and to become a better trumpet. I also wanted to work on time management and getting a project done within a limited amount of time to my best capacity. And I also wanted to work on documentation, because if anyone's seen my code before, I don't comment at all. I don't really like documentation, but I know it's really helpful for work and college, so I'm going to work on that. And for professional experience, I wanted to work and communicate with industry experts and be able to be more comfortable with public speaking, as it's a skill I'll need in the future. So initially for my timeline, I thought I would research from October to November, code from December to January, and for some reason I thought it would take an entire month to design and print a box, which ended up taking about 2 days. And I also thought it would take an entire month to integrate the box in the microcontroller, which took about 30 seconds, because it's literally just putting the microcontroller inside a box. And finally, I thought I would do final testing and presentations in March and April. That did not happen. What ended up happening was I researched from October to January. I researched code, microcontrollers, music theory, and SolidWorks, and I coded from January to March. And while I was still coding in April a little bit too, but as I was coding, I also decided to print and put the box together. And finally, I prepared for final testing and presentations in April. So for my project, I used 4 main components. For my hardware, I used a 3D printer for my box. I used a sound detector to detect sound, and my microcontroller is a SparkFun breadboard, which is really similar to an Arduino Uno, if you're familiar. And for my software, I use Arduino IDE to code. So for my research, I split my research up into 4 main parts. I researched music theory, code, microcontrollers, and CAD. So when we get into music, obviously the way an instrument makes sound is through vibrations. And these vibrations create sound waves, and these cycles of sound waves is what we call frequency. And how humans perceive frequency, or how high or how low the note is what we call pitch. Now, initially I thought I would have to code each instrument separately because obviously an oboe and a trombone sound extremely different. So I thought I'd have to code different instruments. However, the only reason they sound different is because of their timbre, which is their unique aspects of the instrument, so like the way the horn or the bell is shaped, and it makes the instrument sound different. But each instrument, as long as they're playing the same note in the same octave, their frequency is the exact same, so I could just use the numerical values to calculate it for any instrument. And finally, I learned about resonance, which are aspects of the instrument that amplify sound, which basically an instrument takes vibrations, it vibrates at the same frequency, and it amplifies the sound, which is helpful for my code for detecting whether a sound is too quiet for pitch detection. Next, I wanted to make sure that my code could work for any octave. And octaves are basically just exponential frequency jumps. So if I have the note A in the 4th octave, to go up an octave, I would just multiply it by 2, and to go down an octave, I would divide it in half. So I think the calculations for that in my code would be pretty easy. And the note I use for most of my calculations is the international concert pitch, which is an A in the 4th octave. But my code does work for any note. Next, I started to research microcontrollers, and I have no experience with microcontrollers whatsoever. So the first thing I learned was microcontrollers are basically little computational devices that I can upload code into, and it'll run my code for me in the right way. Next, I needed to know the parts that I need for my sound, or for the physical part. So I needed LEDs, resistors, and wires, and I learned what all those components do, and I learned how the current flows through the system through multiple experimentations in Tinkercad. This was when I was first learning how to just blink one light, and then once I got comfortable with that, since my project has 3 LEDs, I learned to blink 3 LEDs separately. Next, I had to research code. So initially for my sound detector, I wasn't going to use a physical mic to do this. I was going to find a library on Arduino IDE and then have that library transform my computer into a speaker or a mic. But instead, all the libraries I found were in Python, or just I didn't know how to use them at all. So I ended up going for a physical mic. So we scratched that. And then the next thing I needed to start learning was C++, because in my use in comp sci, I only know Python and Java, but C++ is pretty similar to Java, so it was a little bit easier for me. And the next thing I needed for my code was an analog to digital converter, which I'll reference as ADC. So basically, what the sound detector picks up is sound waves, but what my code needs is numerical values to compute it. So what this does is just takes those sound waves and finds amplitudes and peaks and everything, and converts those into a numerical value, which my discrete Fourier transform and fast Fourier transform will then use. What a discrete Fourier transform does is it's basically a method that takes numerical values from an ADC and uses it to find the frequency of the note. And what an FFT does is, since a DFT is really computationally expensive, it takes a lot of energy, and it's not efficient, an FFT simply uses a divide and conquer strategy to individually find parts of the DFT and calculate those to make the calculations a lot more efficient. Next, I researched CAD. This was mostly my friend Scarlett helping me through and helping me make the box. So this was the initial design, and this is what I ended up making. There's a hole, you can't really see, but there's a hole right here for the sound detector and 3 lights here. Now that my research was done, I could begin my project. So I started off with the LEDs and sound detector. The first thing I did, since I said I wasn't going to use a library for this, this was the sound detector that I decided to use. It's the spark plug sound detector, and I wired the 3 LEDs and I hooked up the sound detector. However, when I ran my code, which I did before this, when I ran my code, it just did not work. The lights just refused to turn on. And I was freaking out about this for an entire month, fixing the code and fixing it, until I realized something was wrong with the way I plugged in these pins. So I had ground connected to ground, obviously. I had VCC connected to 5 volts. However, I should have had audio connected to A0. Instead, I had gate connected to A0, to A0, and what gate does is gate only sends volume data, so really what my FFT is getting is data about how loud or how quiet it is. It's not getting the full data set that I need to analyze. And so since there was really no real data going to the FFT, it couldn't analyze anything, so it just kind of crashed my code and nothing really worked. So after I fixed that, of course I had more problems. Harmonic overtones might be the bane of my existence. Basically what harmonic overtones are, when a note is played from an instrument, it naturally has multiple layers in it. So the first layer is our first harmonic for the note A in the fourth octave. It's 440 hertz. That's what we normally hear. That's the main harmonic, but there's multiple harmonic layers after that. So we have the next octave as a layer, which is 880 hertz, and the third harmonic is the perfect fifth, which for an A would be an E, which is a 1320 in the sixth octave. And what my code was picking up was the second and third harmonic, which was an issue because even though it would tell me I was in tune, if I tried any other note, it would tell me I was completely off. And it was because it wasn't picking up the correct harmonic. So the way I fixed this is I implemented 3 different strategies. One, I used DC offset removal, which basically DC offset is an extra voltage that comes in with the information from the sound waves, because the way information travels in the microcontroller is through electricity. So there's always a little extra bit of voltage that goes along with it, and that can completely shift the sound wave up or down or left and right, which can make it so that the data is completely off. So I implemented that, which I'll show you when I get to my code. The next solution I use is a Hamming window, which is basically, this is a Hamming window. It's like a little window that reduces spectral leakage from the FFT. And spectral leakage is, so when an FFT is being computed, it makes a bunch of little components, and those extra components can create a mess of the data, and we call that spectral leakage. So having a small little window to analyze everything reduces that and makes everything a little more accurate. And finally, I use peak detection, which basically finds the value, the frequency value, that's most analyzed from the FFT. Next, now that I got that out of the way, I can explain my code. So this first section here, I imported my FFT, I set up my pins and sound detector to certain pins on the microcontroller, and I created parameters for the FFT. So this here shows how many samples the FFT takes at any given time. This shows how many are taken per second, and this is my frequency tolerance, which is how many hertz the note can deviate from a given frequency. And this is the noise threshold, which helps filter background noises. And finally, I have to create 2 arrays for my FFT. When FFT is running, it has 2 components, the real component and the imaginary component. And the real component is the cosine, and the imaginary component is the sine part of the sound wave. But the imaginary component isn't exactly needed when we're computing this, but it's really helpful to have the full set of data. Next, I created arrays of all of my frequencies and their corresponding note names, and I kept track of how many notes I had in total because, well, originally I was really ambitious and I said, I'm going to do all 8 octaves. I really didn't know how, so I ended up just sticking to the 3rd to 5th octaves. Next, I stored everything. My code was having a lot of problems with having enough memory because I kept going over the limit for a SparkFun or breadboard. So what I did was I stored it straight to the program memory, and then now that it's stored in the program memory, to access it, I have to use special variables. So what this does is it copies the note frequency so I can use it for the FFT, and this copies the note name so I can print it to my serial monitor. And then here, this is where I found the strongest frequency, which I used for peak detection. Basically what this does is it uses parabolic interpolation, and parabolic interpolation is basically a concept that's pretty self-explanatory. It basically says that a peak on a parabola lies in between its main frequency and its adjacent frequencies, which I put into separate bins, which are just little smaller ranges of frequency. Next, this part's pretty simple. All I did was set up the LEDs in the monitor, and I had it print the information. Additionally, I added a blink test because halfway through, when it was getting a little too close to tinker with the code, my blue LED just completely stopped working. And I thought this was a huge problem with my code. And I was freaking out about this for 6 hours straight. Turns out the only problem was my LED dying. So that was the only problem. Nothing was wrong with the code. So I set up a blink test so it flashes all 3 lights at once so I know if all LEDs are working so I don't freak out again. Next, I collect the samples, and this section here basically just calculates if the sound that's being detected is a little too quiet, and if it's too quiet, it'll just skip the pitch detection altogether. Next, this is where I find the DC offset and peak detection stuff that I found earlier. This is where I actually subtract it from all my samples, and this is where I run my FFT and use my FFT to find the frequency that it's closest to, and then compares it to find if it's sharp, flat, or in tune. And finally, it sends it to the LEDs and prints everything to the serial monitor. So now that the code's done, here is pictures of the outcome. Obviously, I was testing with 440 Hz, because if you guys couldn't tell, it's my favorite frequency. This is when it was flat, so 440 is the correct one. If it's flat, then 435 would be flat, and it shows here that it's flat. Here is when it's a little too high and it's sharp, and this is when it's flat. And I would also like to do an actual demo for you guys, right here. So we have the tuner right now, and if I were to pull up that exact frequency here, I'm sure a lot of you guys heard this when I was in the back room constantly playing this. Does it sound familiar? Yeah, there we go. So this is in tune. It flashes green. This is flat, 435, so it should be red. And finally, this is sharp. Oh, that's not sharp. There we go. And it should show blue. And that's my presentation. Here's my bibliography. Do we have any questions?
So you said you had like 2 octaves programmed. How difficult would it be to just add the other octaves?
I don't think it would be very difficult at all because basically octaves are just exponential jumps. So to calculate octaves, I'd only have to multiply by 2 or divide. So like 440, if I wanted to jump an octave, it'd be 880, and if I wanted to go down, it'd be 220. So I don't think it should be too hard. It was just, I was kind of struggling to figure this out at first. I was like, you know what, 3 octaves is good for now.
More of a leading question, coding question. You
Yeah.
were saying that, like, you can jump, like, double it, and you can
Yeah.
get the next one. What was the perfect fit thing? Like 13, 15 or something? What?
The perfect fit? Okay, so this is, let me see if I can find it. Somewhere. Oh, here it is. Okay, so these are just harmonic overtones. I don't know why this is, but the second harmonic overtone is an octave, but the third one is not an octave. It's a perfect fit. And a perfect fit is basically when it's 7 semitones up or down from any given note. And a semitone is basically like the flat or the sharp version of a note. So like an A sharp is a semitone of an A. So if we count 7 up from A, we would get an E. And an E in the 6th octave is a 1320.
So what's that harmonic overtone?
So harmonic overtone, it's like different layers of frequencies in a note. So when like an instrument playing a note just naturally produces several layers of frequencies. So the first frequency is like the main layer. That's the one you hear. You hear an A. But there's also these tiny little layers over them, and that's what the harmonics are. And that's what my code was sensing for some reason, which was really confusing, which is why I had everything print to a serial monitor so I could know what frequency was sensing. Yeah.
So what's the range for you actually like being in tune versus like flash green?
Oh yeah. So I said it was a 4 Hz range. So if I would go back to the note 440 Hz, the range for 440 Hz would be 436 to 444. Yeah.
So with the tuner, would you consider adding on like a screen so you can see the note that you're playing?
I was thinking about that actually, yeah. So initially, I was going to add like an LCD onto the thing and just cut a hole out for it, but I wasn't exactly sure how I could do that in the time frame I had when I actually thought about that. So instead of doing that, I just had everything print to this serial monitor on my computer. But I do plan on working on this over the summer, and I will definitely add something like that, so you can print the note that's being played.
You plan on adding anything else?
I do plan on making this a lot smaller because I also plan on not having it connect to my computer because since all the code is uploaded into the microcontroller itself, all I have to do is like hook up a battery pack or some other power source so that I can run it more efficiently, not connected to my computer. And I would add that screen as well.
So I noticed that when you were calculating one of your, like right there, that frame rate,
Yes,
it's off by a little bit.
it is on.
I'm assuming it's by spectral, I believe it's called spectral loss. What was like the loss that you're talking about?
The spectral leakage. I'm
Spectral
pretty
leakage.
sure this might be because of DC offset
Okay.
or spectral leakage. I'm not 100% sure because it is ever so slightly off by like 1 hertz or 2 hertz at a time, which I'm not quite sure why. I think if I had a better sound detector, because these ones are pretty cheap, if I had a better sound detector, a better library than my computer, I think I would be able to get it a lot more accurate.
I was going to ask if you ever considered maybe writing your own fast Fourier transform to maybe decrease there.
I was, and then I realized how complicated fast Fourier transforms really are, and I was like, you know what? There's libraries for that. We're going to use libraries and stuff. But honestly, I might actually do that. That sounds like a fun project over the summer. Yeah.
Do you have a general estimate for how much this project cost you?
So this project for me, it not much. It probably cost like $10 to make because I had all the parts from Combs' back shop. The only thing I had to buy was this sound detector. But if I didn't have that, I'd estimate it to be about $35 to $40-ish. Anything else? Yes.
Are you going to use this like actually in class or during concerts and stuff?
Honestly, I think I might show this to Mr. Farmer to get him to use it because I'm being really serious when I say I hate reading the tiny little lines on music.
Okay, excellent job. Nice. Good job, Souresh.